When you look around the world today, you see electronics everywhere. Whether it's storing your video presentation, analyzing data for your science experiments, or controlling the lights in your house from your phone, we rely on our electronics to store endless amounts of information. As our drive for faster, smaller, and more storage in our electronic devices increase, new material systems are needed to replace the current technology. This is what gives rise to the interest in multiferroics. But what are multiferroics? And how can they solve our current electronic storage limitations? By definition, multiferroics are material systems that combine two or more ferroic ordering properties such as ferroelectricity, ferroelasticity, or ferromagnetism. But for our purposes, we'll be talking about magnetoelectric multiferroics. These are materials that couple ferroelectricity and ferromagnetism for electric field-controlled memory storage. To understand magnetoelectric multiferroics, three concepts need to first come together: ferromagnetism, ferroelectricity, and magnetoelectric effect. First, let's talk about ferromagnetism. Ferromagnetism commonly comes from transition metals with partially filled d orbitals, such as iron, nickel, or cobalt. In a ferromagnet, there is a strong internal interaction that leads to the magnetic moments in a material to align and yield spontaneous magnetization. This magnetization, however, can be changed with an applied magnetic field. As the magnetic field is applied, the orientation of the magnetic dipoles change, leading to a change in the magnetization of the material. This behavior can be shown in a hysteresis loop to show the magnetic field control of their magnetization. Now that we have talked about ferromagnetism, let's talk about the other aspect of multiferroics, ferroelectricity. Conventional ferroelectrics have stable polar phases that are formed by lowering the chemical bond formation, which tends to happen with empty d orbitals. Ferroelectric behavior is very similar to that of the behavior of ferromagnets. Ferroelectric materials have a spontaneous electric polarization where their electric dipoles are aligned. This polarization can be switched by applying an electric field. Like the hysteresis loop of ferromagnets, ferroelectrics have a hysteresis loop that defines the behavior of the polarization by the applied electric field. The last phenomena we need to discuss is the magnetoelectric effect. At the simplest level, the magnetoelectric effect is the coupling between magnetic and electric properties in a material. This can be seen through demonstrations like the simple electric train, where a magnetic field is created from a moving current to push the train through the tracks. In our case, however, it is slightly more complicated. The magnetoelectric effect states that in principle, an applied electric field should induce magnetization in magnetically ordered crystals. For multiferroics, the magnetoelectric effect is seen to be linear and therefore has a simple relation of the polarization is equal to alpha times the applied magnetic field, or the magnetization is equal to alpha times the applied electric field, where alpha is the magnetoelectric tensor. An electric field shifts both the positions of the magnetic cations as well as modifies the electronic wave functions. Both result in a change in the magnetic interactions of the material, primarily due to spin-orbit coupling. In order to actually form magnetoelectric multiferroics, all three of the phenomena must work together in one system. This is often more difficult than one would think because the path to ferroelectricity has the absence of d orbitals, which leads to the absence of magnetism. There are a couple paths, however, to lead to a magnetoelectric multiferroic. One common path is through charge ordering, where a non-centrosymmetric charge ordering in a material leads to ferroelectricity in magnetic materials. Another option for multiferroics is through magnetic ordering. In this case, the ferroelectricity is induced by a lower symmetry ground state that lacks symmetry. Final option, which is the most common path to multiferroics at room temperature, is through the A site. For this multiferroic, the traditional transition metal magnetism is used, while a stereochemical activity of the lone pairs on an A site of a perovskite unit cell leads to the ferroelectricity. The most common multiferroic of this kind is bismuth ferrite. It's also currently one of the only room temperature multiferroics. In this system, the bismuth has a lone pair that allows for the ferroelectricity. However, it has a canted antiferromagnetic moment that forms for the magnetoelectric coupling. In materials like bismuth ferrite, applying an electric field allows for a 180-degree switch of the magnetic moment. When coupled with ferromagnetic films, we can have magnetic spins controlled by electric field. This is how we can potentially solve the energy storage problem. So, multiferroics can be the future.